At 9 o'clock on the night of April 13th, 1970, a control systems engineer named Seymour C. Liebergott sat at console 15 in Mission Control's second-floor operations room in Houston, Texas, watching data streams that suddenly made no sense. The telemetry from Apollo 13 showed electrical power dropping across multiple buses simultaneously, oxygen pressure in Tank 2 falling to zero, and voltage readings that violated every simulation profile he'd studied for 18 months. He'd been monitoring environmental and electrical systems for 55 hours of what had been the smoothest lunar mission NASA had flown, and now his screens displayed impossible combinations of failures occurring 200,000 miles from Earth. Within 90 seconds, he would inform Flight Director Gene Kranz that they were looking at multiple catastrophic system failures on a spacecraft carrying 3 men toward the Moon with no abort option that could bring them home in less than 4 days. Liebergott had trained for single-point failures, double failures, even triple redundancy losses in the simulator. But the pattern unfolding across his console suggested something that shouldn't exist in a spacecraft designed with backup systems for the backup systems. The readings indicated they'd lost their primary source of oxygen, their primary source of electrical power, and their primary source of drinking water all in the same moment, and every procedure he'd memorized assumed at least 2 of those 3 would remain functional. Commander James Lovell, 42 years old and flying his 4th space mission, had just finished a television broadcast from the command module 13 minutes earlier, showing viewers back on Earth how astronauts lived in weightlessness. The networks hadn't even carried it live because by 1970 flights to the Moon had become routine enough that Americans no longer interrupted their Tuesday evening programming to watch. Lovell had flown to the Moon once before on Apollo 8, had orbited Earth on Gemini 7 and Gemini 12, and had accumulated more time in space than any human being alive, which gave him an instinctive sense for how spacecraft were supposed to sound and feel. At 55 hours and 54 minutes into the mission, he was floating near the tunnel connecting the command module Odyssey to the lunar module Aquarius, when he heard a bang that resonated through the hull, followed immediately by the master alarm. Command module pilot Jack Swigert, 38 years old and added to the crew just 72 hours before launch, when Ken Mattingly was exposed to German measles, saw the master alarm light up and heard the tone, then watched his instrument panel as caution and warning lights illuminated in a cascade. Lunar module pilot Fred Haise, 36 years old and assigned to land on the Moon at Frumao crater, was in the lower equipment bay when the spacecraft shuddered, a motion that shouldn't happen in the vacuum of space unless something was venting or exploding. Swigert keyed his microphone to Houston, his voice carrying that test pilot flatness that came from years of training to suppress panic in emergencies. "Okay, Houston, we've had a problem here." Lovell, already moving back toward the command module's main cabin to see the instrument panel, added his own transmission 16 seconds later with slightly different phrasing that would become more famous. "Houston, we've had a problem." The wording difference mattered less than the tone, which mission control veterans would later describe as containing the first hint of genuine concern they'd ever heard from Jim Lovell in 4 space flights spanning 6 years. In Houston, Liebergott was already correlating data points that couldn't coexist under normal circumstances, while Flight Director Kranz began the immediate mental process of categorizing the emergency, determining available time before critical decisions became irreversible, and identifying which of his 21 console positions held information he needed first. The explosion that caused these impossible readings occurred at 55 hours, 54 minutes and 53 seconds mission elapsed time in the service module's Bay 4, where 2 spherical oxygen tanks provided breathing air and fuel cell reactant for the crew. Tank 2, which had shown minor anomalies during ground testing 18 months earlier, had just completed a routine cryogenic oxygen stir requested by Houston to prevent stratification of the supercold liquid. Inside that tank, electrical power flowing through damaged wire insulation had ignited Teflon insulation in the pure oxygen environment at pressures exceeding 900 pounds per square inch, creating an instantaneous pressure spike that ruptured the tank's outer shell. The explosion blew off the entire outer panel of Bay 4, a piece of aluminum honeycomb structure 13 feet tall and weighing 77 pounds, which tumbled away into space along with fragments of insulation, tubing and structural components. The blast's shockwave propagated through the service module's structure, damaged Tank 1's plumbing enough to create a slow leak, jarred the high-gain antenna out of alignment, and caused the entire spacecraft to pitch and yaw as venting oxygen acted like an uncontrolled thruster. None of this structural damage was visible to the crew because the service module sat behind them, its systems accessible only through the control panel and telemetry. What they could see were the consequences registering on their instruments, readings that told them they were losing the resources that kept the command module Odyssey habitable. Fuel cells 1 and 3 showed declining output almost immediately because they required oxygen flow to generate electricity through the chemical reaction of oxygen and hydrogen. The direct oxygen supply to the cabin, which maintained breathing pressure, was drawing entirely from tanks that were either empty or leaking, giving them somewhere between 2 and 5 hours of breathable air depending on leak rates they couldn't yet calculate. Water pressure was dropping because the fuel cells generated water as a byproduct of making electricity, and with fuel cells dying, their water production stopped. Battery power existed as a backup, but the 3 re-entry batteries in Odyssey were designed to provide power for just the final few hours before splashdown, not for the 4-day journey home that would be required if they survived at all. Lovell pressed his face against the left-hand window, the one that could see past the lunar module docked to Odyssey's nose and might offer a view aft toward the service module. What he saw turned his stomach in a way that 4 space flights and 200 hours in orbit hadn't prepared him for. "We are venting something out into space," he reported to Houston, watching a cloud of particles sparkling in the sunlight streaming away from the spacecraft in a continuous plume that told him this wasn't a thruster firing or a normal dump. It was gas escaping under pressure from a part of the spacecraft that wasn't supposed to have any openings, and the physics of rocket propulsion meant that every molecule leaving the ship was pushing them off course, changing their trajectory in ways that would accumulate over 200,000 miles. The rate of the vent suggested a large opening, and the persistence of the plume meant this wasn't a burst disk designed to relieve pressure in an emergency, it was catastrophic structural failure. In mission control, the initial moments of the crisis unfolded in the specific vocabulary that NASA had developed over 9 years of human spaceflight, a language designed to be precise under stress and to separate observation from interpretation. Lifeboat called out each new failure as it appeared on his screens, while electrical, environmental, and communication systems engineer William Fenner at the EACOM console tracked power loads. Guidance officer Steve Bales, who had made the call to continue Apollo 11's landing when computer alarms threatened to abort the first moon touchdown, now watched Apollo 13's guidance platform show drift rates that indicated the spacecraft was tumbling slowly. Retrofire officer Chuck Dieterich began calculating what abort options might still exist, knowing that the standard procedure of firing the service module's main engine to turn around and come straight home assumed that engines still worked and the service module wasn't structurally compromised. Network controller Gary Rennick confirmed they had solid communications through multiple ground stations, which meant whatever was failing hadn't taken out the radio systems yet. Gene Kranz stood at the flight director's console in the center of the room, his white vest marking him as the lead controller for this shift, watching the pattern of failures propagate across mission control's displays, with the recognition that they'd just entered a realm beyond the simulations. Flight directors trained for emergencies by running through scenarios where instructors deliberately failed systems to test crew and ground team responses, but the simulations followed rules that reflected engineering logic. They failed one system or one subsystem or one set of related components. What Kranz was seeing violated that logic, with electrical, environmental, and propulsion systems failing in combination, suggesting a physical event that had damaged multiple separated areas of the spacecraft. He made the immediate call to wave off any procedures that weren't directly related to keeping the crew alive, telling his team to stop the normal timeline of activities and focus entirely on understanding what they'd lost and what options remained. Aboard Apollo 13, Swigert was methodically working through his caution and warning lights, resetting circuit breakers and attempting to restore systems according to procedures that assumed electrical transients or computer glitches, rather than physical destruction. He closed valves, opened valves, reset fuel cell purges, and checked hydrogen tank pressures, following the logical troubleshooting process that assumed the spacecraft was intact. Lovell, floating beside him, watched the main bus voltages continue their steady decline despite everything Swigert tried, and he began to accept what the instruments were telling them, even though it meant something that shouldn't be possible. They were losing Odyssey, not to a single failure that backup systems could handle, but to a cascading collapse of the integrated systems that made the command module habitable. The fuel cells required oxygen they didn't have, the oxygen tanks were empty or leaking too fast to maintain pressure, and the batteries couldn't carry the electrical load for more than a few hours without depleting reserves they'd need for re-entry. What made this crisis fundamentally different from any previous space emergency was the distance and the geometry of their trajectory. Apollo 13 was 200,000 miles from Earth, having already escaped Earth's gravitational well and entered the portion of their flight path where the Moon's gravity was stronger than Earth's. They were coasting toward the Moon at roughly 2,000 miles per hour relative to Earth, on a trajectory calculated to bring them into lunar orbit, where they would have circled twice before descending to the surface. That trajectory, chosen for fuel efficiency and landing site access, meant they couldn't simply turn around and fire their engine to come straight home. The physics of orbital mechanics required that they either fire their engine immediately for a direct abort, which would take nearly 4 days, and required a functioning service module engine they no longer trusted, or continue to the moon and use its gravity to whip them around and back toward Earth, which would take even longer, but required less fuel and less faith in damaged system. The service module's main engine, designated the Service Propulsion System or SPS, was a rocket motor capable of 20,500 pounds of thrust, enough to slow them into lunar orbit or to blast them out of orbit and back toward Earth. It sat directly below the command module, in the center of the service module's cylindrical structure, surrounded by fuel tanks, oxygen tanks, helium tanks, and the fuel cell bay where the explosion had occurred. No one in Houston or on the spacecraft knew whether the explosion had damaged the engine, ruptured its fuel lines, or compromised its structural mounting, and NASA's safety rules were absolute about firing rocket engines that might be damaged because an explosion during the burn would destroy the command module and kill the crew instantly. The SPS used hypergolic propellants, fuel and oxidizer that ignited on contact, which meant there were no ignition systems to fail, but also meant that any leak could create fires or explosions in unpredictable locations. Krantz made the call at 56 hours mission elapsed time, less than 6 minutes after the explosion, that they would not attempt to direct abort using the SPS. The risk of firing a potentially damaged engine was too high, and the unknown state of the service module's structure meant they couldn't trust that the engine would even fire in the right direction. That decision locked them into a lunar trajectory, whether they wanted it or not, meant they would continue coasting toward the moon for the next 40 hours, then use the moon's gravity to swing them around, and start the long fall back toward Earth. It also meant they needed a different engine for any course corrections, and the only other engine available was in the lunar module Aquarius, the spider-shaped craft designed to land 2 men on the moon and return them to orbit. The lunar module had never been intended as a lifeboat. Its systems were designed to keep 2 men alive for 45 hours, not 3 men for 4 days, and its descent engine was meant for landing, not for the kind of trajectory adjustments that would be needed to hit Earth's atmosphere at exactly the right angle to avoid either burning up or skipping back into space. Aquarius became their refuge, not by design but by elimination of alternatives. Laibergot's calculations showed that Odyssey's oxygen would be gone within 2 hours at current leak rates, and electrical power from the dying fuel cells would last even less time. The re-entry batteries couldn't be touched because they'd need every amp-hour to power the command module during the final 3 hours of the mission, when Aquarius would be jettisoned, and only Odyssey's heat shield could protect them through re-entry. That meant shutting down Odyssey completely, leaving it as cold and dark as the space around them, and moving the crew into Aquarius, where the lunar module's descent stage carried oxygen, electrical power, water, and a rocket engine they could use to adjust their course. The procedure for powering down a command module in space didn't exist in any manual because no one had imagined needing it. Every scenario ended with either using the command module to get home or dying before power became an issue. The decision to use Aquarius as a lifeboat required calculations that cascaded through every system on both spacecraft and every console in mission control. Telmu controller Robert Hesselmeyer, responsible for lunar module electrical and environmental systems, began working out how to stretch consumables designed for 45 hours across 90 or 100 hours. His initial numbers were brutal. The oxygen margin was acceptable because the lunar module's descent stage carried enough for the extended mission, but electrical power was desperately tight and water was worse. Aquarius generated electricity from 4 silver zinc batteries in the descent stage and 4 more in the ascent stage, with a total capacity designed to run the lunar module's guidance computer, environmental controls, communications, and instruments for less than 2 days. Extending that to 4 days meant shutting down every non-essential system, reducing the electrical load to barely more than what the guidance computer and radios required, and letting the cabin temperature drop to whatever ambient level resulted from the sun's heating on one side and space as cold on the other. Water was even more constrained because the lunar module's cooling system used water evaporation to remove heat from electronics, then vented the water vapor overboard. Under normal landing operations, that system kept computers and radio transmitters from overheating during the high-power descent phase. For a 4-day mission as a lifeboat, the water cooling system would drain their 39 pounds of water reserves in less than 2 days, leaving nothing for drinking and nothing for the cooling system's final hours when they'd need to power up multiple systems simultaneously. Hesselmeyer calculated they'd need to reduce electrical loads enough to minimize cooling requirements, which meant putting Aquarius into what he started calling deep sleep, a minimum power configuration that kept the crew alive and maintained communication, but did almost nothing else. The guidance computer would run continuously, because turning it off and restarting it would drain batteries through the initialization process. But they'd shut down platform heaters, cabin fans, all unnecessary lighting, and every switch panel they could afford to leave dark. Lovell and Haise began the process of powering up Aquarius at 57 hours into the mission, working from a checklist that normally took 3 hours and had to be completed in 15 minutes before Odyssey's oxygen ran out. They were activating systems in an order that violated the careful sequencing NASA had developed, bringing computers online before cooling systems were fully active, initializing guidance platforms before proper warm-up cycles, and skipping checkout steps that would have verified everything worked correctly. Haise, who trained for 6 months to land this lunar module on the moon, now powered it up knowing they'd never fire the descent engine for its intended purpose, and knowing that everything he activated was consuming battery power and water they couldn't replace. The lunar module's cabin filled with the sound of cooling fans, computer relays and radio static as systems came alive, while through the tunnel behind them, Odyssey was going quiet as Swigert shut down panel after panel, preserving battery power for the re-entry that was 4 days away, if they could survive that long. The geometry of their situation was unforgiving in ways that became more apparent as the ground team worked through abort calculations. Retrofire Officer Dieterich had determined that even with Aquarius's descent engine, they couldn't significantly speed up the return trip without consuming propellant they'd need for final course corrections. The lunar module's descent engine could produce 10,850 pounds of thrust at maximum, enough to slow a landing or to make trajectory adjustments, but not enough to dramatically change their velocity relative to the moon. They were locked into the same basic flight path they'd been following, a long coast to the moon that would take another 40 hours. A gravity swing around the lunar far side that would take 90 minutes, and then a longer coast back to Earth that would require 80 hours at current trajectory. The earliest possible splashdown would be late Friday afternoon, April 17th, assuming they could make all the required engine burns with a spacecraft never designed for the job. By 58 hours mission elapsed time, 94 minutes after the explosion, Apollo 13 was in a configuration that resembled no spacecraft humans had ever flown. Aquarius was powered up and serving as the active control station, with Lovell monitoring its systems and Haise working with Houston to configure the guidance computer for a trajectory it was never programmed to lie. Odyssey was shut down to minimum systems, its cabin already cooling toward the freezing temperatures it would reach without fuel cell heat, with only essential equipment left energized. Swigert was systematically documenting the shutdown procedure, writing down every switch position and circuit breaker configuration, because they'd have to power Odyssey back up before re-entry with no mistakes and no way to test anything beforehand. The service module remained attached behind Odyssey, damaged and venting, its structural state unknown, but suspected to be catastrophic based on the violence of the explosion and the persistence of the gas leak. The first critical engine burn came at 61 hours 30 minutes, a course correction using Aquarius's descent engine to adjust their trajectory for the correct lunar flyby. Without this burn, they'd still go around the moon, but they'd miss Earth entirely on the return trajectory, sliding past the planet into a permanent solar orbit that would become their tomb. The burn needed to be precise within seconds of duration and fractions of a degree in pointing accuracy, which required attitude control with a spacecraft that was now 58 feet long from the command module's nose to the service module's engine nozzle, weighing 43 tons. And responding to control inputs completely differently than the lunar module's guidance system expected. Aquarius's autopilot had been programmed to control a vehicle that weighed 33,000 pounds during landing, not 95,000 pounds docked to 2 other spacecraft. Haise hand flew the attitude alignment using Aquarius's small reaction control thrusters, 16 small rocket engines scattered around the ascent and descent stages that could provide precise rotation control. Each thruster firing consumed propellant they'd need for later corrections, and the mass distribution of the docked spacecraft meant that rotations required longer burns than normal because the heavy service module behind them created a long moment arm. He aligned the spacecraft by looking through the lunar module's small triangular window, finding specific stars that marked the correct orientation, while Lovell monitored the guidance computer's solution for any errors that would indicate platform drift or failed systems. The 2-hour burn lasted 30 seconds, long enough to change their trajectory by 840 feet per second, ensuring they'd hit the entry corridor that would bring them into Earth's atmosphere at the correct angle. In Houston, teams of engineers were already working problems that wouldn't become critical for 2 or 3 more days, but needed solutions developed now. The primary concern was carbon dioxide, the gas humans exhale with every breath, which becomes toxic at concentrations above 4% and lethal above 10%. Spacecraft removed carbon dioxide from the cabin air using lithium hydroxide canisters, chemical filters that absorbed CO2 until they became saturated and had to be replaced. Odyssey's command module carried canisters designed to support 3 men for 9 days, but those canisters were square. Aquarius carried canisters designed to support 2 men for 2 days, and those canisters were round. The lunar module's CO2 scrubbing system was adequate for the crew's immediate needs, but projections showed they'd exhaust the available round canisters by Thursday morning, 36 hours before splashdown, and without scrubbing, carbon dioxide would build to lethal levels within 6 hours after that. The engineers needed to design an adapter that would let them use Odyssey's square canisters in Aquarius's round receptacles, using only materials and tools available aboard the spacecraft, and they needed to design it, test it on the ground, and communicate the procedure to the crew before CO2 levels began climbing past safe margins. Power consumption tracking became an hour-by-hour counting exercise that occupied multiple engineers throughout the mission. Every system aboard Aquarius drew power from the 8 silver-zinc batteries that were their only electrical source, and every amp-hour consumed brought them closer to running out of electricity before they could get home. The guidance computer drew 35 amps continuously. The radio transmitter drew 14 amps while transmitting cabin fans drew 6 amps. Instrument displays drew another 12 amps across all panels, and dozens of smaller systems added fractional loads that accumulated into significant drains over hours. Hisselmeyer and his team calculated that at normal lunar module power consumption, they'd exhaust the batteries on Wednesday night with more than a day still remaining before splashdown. The deep sleep configuration reduced total draw to roughly 15 amps, low enough to keep systems alive through Friday afternoon. But that calculation assumed nothing unexpected drew additional power and no emergencies required powering up backup system. The temperature inside both spacecraft began dropping within hours of the shutdown, a consequence of eliminating the waste heat from fuel cells and from electronics that would normally keep cabins warm. In Odyssey, now completely unpowered except for a single 5-amp heater protecting the re-entry guidance computer, cabin temperature dropped through 50 degrees Fahrenheit on Tuesday evening and continued falling toward the point where water vapor in the air would condense on cold surfaces. In Aquarius, running at minimum electrical load, the sun's heating through windows on one side, and the cold of space radiating from shadowed surfaces on the other, created temperature gradients that ranged from near freezing at the floor to merely cold at eye level. The crew wore their thin cotton flight suits, inadequate insulation against temperatures that would eventually reach 38 degrees. Because their pressure suits were stowed in Odyssey's lower equipment bay and retrieving them would require entering the freezing dark command module and consuming time and energy they couldn't spare. Water rationing began immediately after the decision to use Aquarius as a lifeboat, with Houston imposing a limit of 6 ounces per man per day, 1/5 the normal consumption rate, and barely enough to maintain hydration. The restriction was driven entirely by the cooling system's requirements, which used water evaporation to remove heat from electronics and would otherwise consume the entire 39-pound water supply within 48 hours. By running at minimum power, they'd reduced cooling requirements to the point where the system would theoretically leave enough for the crew to drink. But the margin was so tight that every extra hour of operation, every additional system activation and every unplanned transmission drew from the same water supply that was keeping the crew alive. Swigert, Lovell, and Haise began rationing their water consumption to 4 ounces per day, voluntarily, accepting dehydration as a lesser risk than running out of water for cooling during some future emergency. The lunar flyby occurred on Tuesday night, April 14, 1970, when Apollo 13 passed behind the Moon at 77 hours mission elapsed time, and emerged from the far side 90 minutes later, having used the Moon's gravity to whip them back toward Earth. The crew could see the lunar surface passing beneath them at an altitude of 158 miles, far higher than the 60 nautical mile orbit they would have entered for landing. Close enough to make out crater details and mountain ranges in the oblique sunlight. Lovell looked down at the Fralmaro highlands where he would have landed, the rolling terrain that held ancient lunar samples ejected from deep craters and scattered across the surface by billions of years of meteorite impacts, and he realized he'd flown to the Moon twice and would never walk on it. Haise, trained to land the lunar module and conduct the first geological traverse across a highland region, watched his landing site recede as they swung around the moon's eastern limb, knowing that his chance was gone and might never come again because NASA couldn't afford to launch missions that didn't succeed. They executed the second critical engine burn at 79 hours 27 minutes, 2 hours after emerging from behind the moon, using Aquarius's descent engine to accelerate their return and adjust the trajectory for a Pacific Ocean splashdown. This burn was longer than the first, 4.5 minutes of sustained thrust that added 860 feet per second to their velocity and shortened the return flight by more than 9 hours. The descent engine performed exactly as designed, its constant thrust pushing them deeper into their seats as Aquarius's computer controlled the burn duration and shut down the engine at precisely the correct moment. The fuel consumption was enormous, more than 40% of the descent stage's propellant, but the calculation was simple. Getting home faster reduced the time they'd need life support and reduced the cumulative risk of additional system failures. Communication with the ground became increasingly difficult as they moved farther from the moon, and the limited power available for the radio transmitter forced them to use low-gain antennas rather than the high-gain dish that normally provided clear voice and telemetry. Low-gain antennas were omnidirectional, receiving signals from a broad area of sky rather than focusing on Earth's location, which meant weaker signal strength and more noise in the transmission. The crew's voices became scratchy and broken during some passes, forcing Houston to repeat commands multiple times and requiring the crew to keep transmissions brief to save battery power. Mission Control compensated by scheduling communication windows around tracking station passes that offered the strongest signals using NASA's global network of ground stations in California, Spain, and Australia to maintain contact as the Earth rotated beneath them. The carbon dioxide problem reached crisis level on Wednesday morning, April 15th, when sensor readings showed cabin CO2 concentration climbing past 2% and accelerating toward the 3% level that would begin causing headaches, confusion, and impaired judgment. The engineering team in Houston had worked through Tuesday night, testing different adapter designs using hardware identical to what was aboard the spacecraft, and they'd found a solution that used a sock, the cover from a flight procedures manual, duct tape, and the stiff cardboard from a command module, lithium hydroxide canister box. The procedure required 30 minutes of assembly work, and when Swigert built the contraption following Houston's instructions, it looked like a desperate jury rig that no engineer would trust. But the numbers worked because the adapter created enough surface area contact between the square canister and the round opening to pull cabin air through the lithium hydroxide and scrub out CO2. Within 2 hours of installing the first adapter, cabin CO2 readings dropped back below 1% and stabilized, buying them the breathing time they'd need to survive until Friday. Sleep became nearly impossible in the cold, dark cabin, with 3 men sharing a space designed for 2, in zero gravity that required strapping into sleeping bags or wedging into corners to avoid floating into equipment. They worked in rotating shifts with at least one person awake at all times, monitoring systems and ready to respond if Houston called. But the shifts degraded into exhausted half-sleep where closing your eyes didn't produce rest because the cold penetrated everything, and adrenaline kept minds racing through failure scenarios. Lovell, who'd flown space missions totaling more than 700 hours and had learned to sleep in orbit, found himself lying awake listening to the cabin's sounds, the hum of cooling fans, the click computer relays, the occasional hiss of a thruster firing to maintain attitude, trying to identify any new sound that might indicate another system failing. By Thursday morning, April 16th, they were halfway home with 36 hours remaining before splashdown, and the cumulative effects of cold, dehydration, and sleep deprivation were beginning to show in crew performance. Swigert's transmissions became shorter and more clipped. Lovell took longer to respond to Houston's questions, and Haise developed a urinary tract infection from the combination of dehydration and inadequate hygiene facilities, causing fever and chills on top of the cold everyone was experiencing. Mission Control had medical staff monitoring crew voices for signs of cognitive impairment, listening for slurred words or confused responses that would indicate carbon dioxide buildup or severe dehydration. But the crew remained functional even as they approached the limits of human endurance. The final major course correction came at 105 hours 18 minutes. Another descent engine burn, lasting less than 15 seconds, that fine-tuned their trajectory for the correct entry angle. Earth's atmosphere is only about 60 miles thick on the scale that Apollo was traveling, which meant their trajectory had to hit a corridor less than 2.5 degrees wide, steep enough to avoid skipping back into space, but shallow enough to avoid burning up from excessive deceleration. The entry corridor had an upper boundary at -5.5 degrees and a lower boundary at -7.7 degrees, and even after all their burns using Aquarius's engine, they were tracking half a degree too shallow, which would cause them to skip off the atmosphere and sail past Earth into a solar orbit. The correction burns steepened their angle by 1 degree, centering them in the corridor with enough margin to survive errors in the final guidance. The preparation for re-entry required powering up Odyssey from its 3-day cold sleep, a procedure that had never been done before and carried risks that accumulated with every switch they'd throw. The command module's guidance computer needed several hours to warm up and initialize before it could accept the state vector, the precise position and velocity information that would guide them through re-entry. Critical components had been at freezing temperatures or below for more than 80 hours, and no one knew whether circuit boards, switches, relays, or displays would work properly after that kind of cold soak. Water condensation on electrical panels was a particular concern because it could cause shorts that would blow circuit breakers or damage systems they'd need for the final hours. The power-up procedure had to be timed perfectly to finish with enough margin before entry that they could troubleshoot problems, but late enough that they didn't exhaust the re-entry batteries by running systems unnecessarily. Swigert began the Odyssey power-up at 133 hours mission elapsed time, 8 hours before splashdown, working from a completely new checklist that engineers had written over 3 days by testing every step in the command module simulator in Houston. He worked methodically through panels that had been dark since Tuesday night, closing circuit breakers, activating switches, and watching displays come alive with instrument needles swinging to their proper positions. The guidance computer initialized correctly despite the cold, its circuits warming under their own power draw, and beginning the gyroscope spin-up that would give them attitude reference for entry. Radio systems activated and locked onto ground transmitters, showing that the long-range communications they'd need for re-entry were functional. Electrical buses showed proper voltage as battery power flowed through distribution systems that had been dormant for 76 hours. One by one, the critical systems proved they'd survived the cold, and the command module began its transformation from a frozen shell into a functioning spacecraft. The configuration for entry required jettisoning both the service module and the lunar module, separating Apollo 13 into its component pieces so that only the command module Odyssey would attempt re-entry, with its heat shield protecting the crew. The service module's separation came first at 138 hours mission elapsed time, explosive bolts firing to release the cylindrical structure that had provided propulsion, power, and life support for most of the mission. As the service module drifted away, the crew got their first look at the damage from Monday night's explosion, and what they saw confirmed that firing the SPS engine would have killed them. The entire outer panel of Bay 4 was gone, ripped away by the blast and exposing the interior structure, and visible damage extended to adjacent bays where the explosion's shock wave had buckled metal and torn insulation. Lovell photographed the damaged service module as it tumbled away, documenting the failure for the investigation that would determine what went wrong and how to prevent it from happening again. The lunar module jettison came later, less than an hour before entry, and it carried emotional weight beyond its technical necessity. Aquarius had kept them alive for 3.5 days, provided the propulsion they'd needed for course corrections, and served as home in conditions it was never designed to endure. Haise, who'd trained to fly Aquarius down to a lunar landing, and who'd lived in its cramped cabin longer than any human ever had, floated back into Odyssey for the last time and sealed the tunnel hatch. The explosive bolts fired, springs pushed the lunar module away, and they watched through Odyssey's windows as the spider-shaped craft that had been their lifeboat drifted back into space, its mission complete even though it never landed on the moon. Within hours, Aquarius would burn up in Earth's atmosphere over the Pacific, its lunar structure melting in the heat that Odyssey's heat shield was designed to survive. 3 men now sat in Odyssey's cabin in positions they'd occupied for launch 5 days earlier, strapped into couches that faced heat shield first as they prepared for entry. Their pressure suits, retrieved from Odyssey's storage bay, provided insulation against the cold and would protect them if the cabin lost pressure during entry. The re-entry guidance program ran in the command module's computer, monitoring their trajectory and ready to fire reaction control thrusters to maintain the correct attitude for heating. Communication through ground stations became intermittent as they descended toward the entry interface at 400,000 feet altitude, where the atmosphere would become dense enough to begin heating the spacecraft and creating the ionization blackout that would cut off all radio contact for 4 minutes. Entry interface occurred at 142 hours 40 minutes mission elapsed time, with Odyssey traveling at 36,000 feet per second, nearly 25,000 miles per hour, and beginning to feel the first hints of deceleration as the atmosphere compressed ahead of the heat shield. The acceleration built slowly at first, pressing them back into their couches with forces that felt gentle after the violence of launch. but would build to 6 times normal gravity at peak heating. The spacecraft began to glow as friction heated the ablative material on the heat shield to more than 5,000 degrees. Hot enough to melt steel, with the heat shield designed to burn away in controlled fashion while conducting minimal heat through to the crew cabin. Through the windows they could see orange and yellow plasma flowing past, chunks of ablative material tearing away and streaking behind them, and the whole spacecraft shaking with buffeting as they plowed deeper into thickening air. The ionization blackout began at 142 hours 43 minutes, cutting off all communication with Houston as superheated plasma around the spacecraft blocked radio signals. Mission Control had expected 3 minutes of silence during the blackout based on nominal entry trajectories flown by all previous Apollo missions, and controllers watched their countdown timers, knowing that if they didn't regain contact within 4 minutes, something had gone wrong, and Odyssey had burned up or skipped back into space. Jim Krantz, back on duty as flight director for entry, watched his console clock count past 3 minutes, with no signal from Odyssey, then past 3.5 minutes, as controllers began exchanging glances that asked the question no one wanted to voice. At 4 minutes the room had gone completely silent, every person watching screens that showed no signal, no telemetry, no voice communication, and beginning to accept that they might have brought the crew this far, only to lose them in the last minutes. The call came through at 4 minutes 27 seconds after blackout began. The longest communications loss in Apollo program history, with Swigert's voice breaking through the static to report they were under parachutes and descending normally. The plasma had cleared enough for radio signals to penetrate, and Odyssey's 3 main parachutes had deployed exactly as designed, the red and white canopies blossoming to slow their descent from 300 miles per hour to 20 miles per hour for water impact. Mission Control erupted in applause. Controllers shouting and pounding consoles and shaking hands with the release of tension that had built over 4 days of impossible problems and improvised solutions. The television networks carried the final minutes live, showing the command module's descent captured by recovery aircraft, and an estimated 40 million people worldwide watched as Odyssey hit the Pacific Ocean at 142 hours, 54 minutes. Mission elapsed time tilted to the stable 2 position with the hatch above water, and began transmitting that all 3 crew members were alive and healthy. Recovery helicopters from the aircraft carrier USS Iwo Jima reached Odyssey within 45 minutes, and swimmers attached a flotation collar to stabilize the spacecraft while the crew opened the hatch. Swigert emerged first, then Lovell, then Haise, all 3 showing signs of their ordeal, with Haise running a fever from his infection, but able to climb into the recovery basket. The helicopter lifted them to Iwo Jima's deck, where they walked off under their own power, dehydrated and exhausted, but fundamentally healthy after 5 days, 22 hours in space, most of it spent in conditions that pushed the absolute limits of spacecraft life support capability. The investigation into the explosion began while Apollo 13 was still returning home, with engineers analyzing telemetry from the moments before the failure and reviewing the service module's construction and testing history. What they found was a cascade of small errors and overlooked anomalies that accumulated into catastrophe. Oxygen Tank 2 had been installed in the Apollo 10 service module in 1968, then removed during modifications and dropped about 2 inches during the removal, a minor incident that was documented but didn't trigger detailed inspection. That drop had jarred loose some internal support structures and damaged a fill line, though the damage wasn't detected during subsequent testing. The tank was then installed in Apollo 13's service module and put through normal ground testing. But during one test the heater thermostat failed to open properly, and the tank's internal temperature rose to over 1,000 degrees Fahrenheit instead of the design limit of 80 degrees. That excessive temperature damaged Teflon insulation on electrical wires inside the tank, leaving bare copper exposed in places. But the damage wasn't visible during external inspection. When Swigert activated the routine cryo-stir on Monday night, April 13th, electrical current flowing through those damaged wires created sparks in the pure oxygen environment inside Tank 2. The sparks ignited the damaged Teflon insulation, and the resulting fire caused a pressure spike that ruptured the tank's outer shell in an explosion violent enough to blow off the Bay 4 panel and damage adjacent systems. The investigation's final report documented every failure in the quality control process that should have caught the damage, every test that should have revealed the problem, and every procedure that would be changed for future missions to prevent similar cascading failures. The Accident Review Board made dozens of recommendations, including redesigning the oxygen tanks, changing the thermostat specifications, improving wire insulation, and implementing more rigorous inspection procedures. Apollo 13 returned 3 men alive from 200,000 miles in space after an explosion that destroyed their primary spacecraft, using a lunar module as a lifeboat for 3.5 days in conditions it was never designed to handle, and bringing them through entry in a command module that had been shut down in space longer than any spacecraft before or since. NASA officially classified the mission as a successful failure, failed in its goal to land on the moon, but successful in demonstrating the system's procedures and human capability that made survival possible when nothing went according to plan. The mission established procedures for spacecraft emergencies that would become standard for all future flights, proved that lunar modules could serve as emergency lifeboats, and demonstrated that mission control teams could solve unprecedented problems in real time with engineering precision and crew trust. Every subsequent Apollo mission carried modified oxygen tanks with improved safety systems, additional emergency procedures for powering down and restarting the command module, and enhanced capability for using the lunar module as backup life support. Apollo 14 flew to Fra Mauro crater 10 months later, and completed the landing that Apollo 13 would have made, collecting samples and conducting experiments that advanced lunar science, but always with the knowledge that getting there and back safely mattered more than any scientific objective. The Apollo program continued through Apollo 17 in December 1972, landing 12 men on the moon over 6 successful missions, and every one of those missions carried lessons learned from the cold, dark hours when 3 men and hundreds of engineers proved that impossible problems had solutions. If you had enough time, enough talent, and the absolute refusal to accept that anyone was going to die in space on your watch. If you found this story of human problem-solving at the edge of survival as compelling as I did researching it, subscribe to this channel where we document the Cold War's technological confrontations and the moments when engineering excellence meant the difference between disaster and survival, and where every video brings you deep into the verified history that shaped our world with the same level of detail and accuracy you just experienced.